Next, we're going to talk about a different type of analysis called mesh analysis. And I just want to mention that usually you would just pick one type of analysis to approach a problem. And so in some cases, node analysis may be the fastest approach, and others, mesh analysis may be another approach that might be faster. So we'll teach them all, but when you're attacking a circuit, trying to solve it, you pick the best one that will give you the result the fastest. And there are many ways to solve a single circuit. So with that, let's talk about mesh analysis. So the first thing is we need to define a mesh. We've already talked about node. That's actually a pretty simple concept. But mesh is a little bit different. So in this approach, what we're doing is we're doing the dual problem of what we already did. We're taking unknowns, so we're identifying, find unknown, we call them mesh currents. And a mesh current is when you have your circuit and it's in a planar form. So it should be in planar form. And this means that there's no jump overs in the circuit. So the one shown on the left here is already in that form. So there's no jumping over in it. And from here is what we can see is that each of the little essentially loops or squares. So let me show with the mouse here. This loop here, that's a mesh. And we can define a current that flows all the way around the mesh. And this sometimes gets a little bit confusing for people. The mesh current is not necessarily each branch's current, but it is the equivalent circuit that would be going in a loop. And then we'll go to the next one. So, okay, so let me draw over this. Here's our mesh current. It goes, actually I'm gonna draw it through here. So the image here, I'll erase this in a second. The image here draws a loop, but it's going all the way through here. And then we also have another mesh current that is going through here. And that is the I2. So we define I1 and I2, and the mesh currents are going through them. And the interaction, so I just want to point out one thing in this image, is the current through this branch, for example, is not just I1 or just I2. It would be the combination of those two. In fact, it would be I1 minus I2. So it's kind of, the way I like to think about it is it's like a current in an ocean or in a body of water. And then when those currents get close to each other, they'll interact. So they'll, in this case, they would take away from each other. So this branch current will not be the same exact as I1 or I2. It'll be a combination of them. Okay, so let's continue with the process. And if it didn't make sense yet, hopefully it will soon. So first we need to find the unknown mesh currents. Before, when we did node analysis, let me find this thing here. We had to name a reference. For mesh analysis, there's not really a reference current. They just flow in a circle. So there's no reference. But what we can do is use suppression, source suppression, to identify the number of unknown currents, mesh currents. So suppression, so use suppression to help identify. Okay, so we've drawn like I1, I2, those are mesh currents, but are they independent? Well, we can use suppression if we're not quite sure. And so we can go to our voltage sources. Those, when they're suppressed, become zero shorts. So we short here, and we short here, and we see that we have the same loop currents. So we'd have two independent ones here. If we suppress the sources and we get like an open, the current cannot flow, that's when we know that it would not be an independent one. So here we have I1 and I2 are two independent ones. So let's erase these suppression. Now we ignore suppression. It was just a tool we used. All right, so now we have two unknown mesh currents here. And what we do is instead of applying before we did KCL, it'll be KVL. So apply KVL around each loop. So I'm going to call it the loop. So it's following the mesh current itself. And one thing that can get confusing is that we're going to follow the current around it. I'm going to change colors here real quick. Maybe we'll go to a bright red. So the current is going to be going, so I1, going through here. And so when I do each one, we're going to label the positive and negative because it's a passive component. So the current's going through it. It's going to be positive to negative, up this way, positive to negative, and I'm going to label this one positive to negative. So all we do is we go around the loop, and then we're going to call this I1, just kidding. Yeah, we're going to call this for I1, just to keep everything straight. And then 0 is going to be equal to, we're going to add up the voltages around the loop. And so here, I kind of have to start from somewhere. So we're going to start from here, go here, it goes down, and it's V equals IR. So it would be a negative I1, R2 here. Sorry, I cannot write. Then we'd be going up, so this is negative to positive, so it would be plus VS1. We'd be going down again here, so it would be minus I1. I1, R1. And then the last one, again, would be going down. So minus so let me make a point here. We're going to be something, the current that's going through it times R3. Note here that the current going through here is I1, but minus I2 because it's flowing in the other direction. So this would be I1 minus I2. Remember, it's okay to write these because these are unknown variables. We're going to solve for them. So we're looking for two equations to solve for two unknowns. Okay, so that would be the full, once you get around to the end, you're done with KVL. Okay, so then we're going to go to the next one, and my suggestion is to kind of ignore everything that we just did and just start again with I2. Okay, so we have 0 equal to, and just pick a place to start. Actually, this time we're going to start up here. So I'm going to go this way. So this one is going to be minus, because we're going down, VS2. And our current's going in this way. And so this is positive, negative. I'll go each one. So then it would be I2 plus I2, R4. Keep going around. Our current is, again, defined in this direction, so it would be positive to negative over the passive element. So it's plus I2, R5, and then plus, and this is where it's going to get a little confusing. Because we're following I2, we're going to redefine, because we're looking at the current, or defining the current in this direction, this as positive, negative. If the value is actually the other way, the polarity, it would just become a negative value. But because we're going in a loop and we're writing the KVL, we have to kind of follow the same direction as I2. So then here we would get over R3, so we're going to have something here. This is going to be R3. And this is going to be, now we're looking at it from this direction, so it's going to be I2 and then minus I1. So it's actually backwards, the opposite direction, I2 minus I1 when we've defined the current in this direction. Okay, and then we've made it back to the beginning point, so that's our full KVL equation. Okay, So let's look at our known values again. So our known values are all the resistor values. So I'm going to just underline them if I can find my mouse over here. Maybe that's too bright. Let's get yellow, paint orange here. Okay, so here it is. R2, R1, R3, R3, R5, R4. Those are all given in the equations. We already know those. And then we also know the voltage source values. So that's going to be VS1 and, oh, did I forget? Oh no, VS2. Here it is. So those are all known values. And then we just want everything else in terms of the unknowns. And we'll do those in purple. So I1 and I2 are our unknowns that we want to solve for. So I1 and I2. I1 and I2. Okay, I just do this to really show that everything has to be written in I1 and I2, which are what you're solving for, or a known value. So in these two equations, everything is accounted for. So now we can go to the final step of the math. Now it's set up as a math equation. You just solve it like a math equation. So solve system of equations. Okay. One thing I forgot to mention is that when you are setting up the mesh currents, the convention is that you always do the same direction. So here, notice that these are clockwise. So you also want to define I2 to be clockwise, I3 to be clockwise, however many you have. If you do it in the opposite direction, technically the math will all work out, but just to keep things straight, it's recommended to use all the same direction and then look at, follow the direction of the current when you're defining the polarity for that specific loop that you're looking at. Okay, so if it's a nice mesh shape, we can use suppression to identify all the mesh currents, how many of them are unknowns, and then apply KVL around them, solve the system of equations. Then you'll have all the current values, and from there, you can define any of the voltages around the loop as well. So that's the basics of mesh analysis.